All right, hello everyone. So what I'd like to do is have a bit of a deeper discussion about this really important concept of work. The idea that work is a force acting through a displacement, and its effect on an object is to transfer energy. Okay, and so it's one of nature's energy transfer mechanisms. Now, what we considered before was the simplest possible example you could imagine. We had a block which can store energy in the form of energy of motion, kinetic energy, and we applied a force to that block, and it was in the horizontal direction. Let's suppose the horizontal to the right is the x direction. So the force had an x component, and we made a simplifying assumption that that force being applied in the x direction is constant. Okay, so we're going to lift that restriction, consider non-constant forces, generalize it in just a little bit. Now, while that force was being applied in the horizontal direction, the block also underwent a displacement from here to here. Okay. So the displacement of the block was from that point to that point, and so the displacement vector is delta x to the right. And what we discovered is that the work done, the effort put in to that action, into that process, is the force times the displacement. And we discovered that the effect of that process, of that force acting through that displacement, what it did was it transferred kinetic energy to the block. So there was a change in the kinetic energy of the block. Okay, so the force and displacement were in the same direction. So this is positive, and so there was an increase in the kinetic energy of the block. Through our efforts, we transferred energy to the block, kinetic energy. Now what we want to do is generalize this situation to forces not just in the x direction, but in any three-dimensional direction, and not just displacements in the x direction, but displacements in a general three-dimensional sense. Okay, and so we're going to take the force and we're going to make it a general three-dimensional vector. However, we're going to retain this restriction that that force be constant. Again, we're going to generalize to non-constant forces a little bit later. Okay, and so now our situation looks something like this. We've got a block, and suppose that we're exerting a force not just to the right, but a force in a general three-dimensional direction in space. And let's suppose that remember that we're not saying anything about the initial and final velocities of the block. The block could have initially been moving downwards, and under the action of that force, the trajectory, bends like this. And so while that force was acting, the block was on some trajectory like this. All that counts is that it started here and, say, ended over here. So the block ends up, say, a little while later, down here. And so the displacement of the block is a vector which points from this point to this point. So that's delta r, the vector displacement in a general three-dimensional direction. So if this is an origin point, this is r initial, this is r final, and delta r is r final minus r initial is that three-dimensional displacement vector. So now what we want to do is generalize this formula for work, effort expended, to this three-dimensional case. Okay, so what we recognize is that the work done is a scalar. Okay, it's not a vector. But we have two vectors to deal with. So the question is there a natural way to combine two vectors, f and delta r, to form a scalar? Well, the obvious answer is the scalar dot product. Okay, and so our guess would be that this is just the vector f, vector dot product with the displacement delta r. And this immediately makes sense. We can see that it reduces to this when we suppose that the force has only an x component and the displacement delta r has only an x component delta x. Then the vector dot product f dot delta r will become fx delta x. Okay, so our generalization reduces to the previous case, and all of this makes sense. Okay, so what we're going to do is we're going to check this out actually in various special cases to make sure that it really makes sense. But now just remember, from a vector dot product, what is this? Well, it's the magnitude of that constant force vector that's been acting times the magnitude of the displacement vector, which we'll call d, times cosine of the angle between those two vectors, which we'll call theta. Okay, so we are proposing that this is a generalization of the concept of work, effort expended, to to this more general situation. Now let's see if this makes any sense. So what we're going to do is we're going to look at 4 different sort of special cases, kind of limiting cases, sort of extreme cases of this definition, and see in each case whether it still makes sense to us. Okay, so first of all, let's consider the case that the displacement is equal to 0. Okay, well, if the displacement is 0, delta R is 0, well then the work done is equal to 0. So if displacement is 0, tells us that the work done is equal to 0. It tells us that the energy transferred, remember that work is energy transfer, it tells us the amount of energy transferred must have been equal to 0. So a really nice example of this, a simple example of this, is to imagine a block. So here's our block, but that block is not free to move. That block is, bolted to the floor. Okay, and so we've got a person over here, and this person is, this person is applying a force to the block, pushing really hard on the block like this. Okay, but that block isn't doing anything. The displacement delta R of the block is equal to 0. It's not moving like this. And so according to our definition, that says that the work done is equal to 0. Now you think about that and you think, well, that doesn't quite make sense, because if I'm pushing on a block that doesn't move and I push really hard, I'm going to start sweating, okay? And I'm going to use up chemical energy, and I'm going to heat up. Like, there's all kinds of stuff. It feels like I'm doing work, okay? I'm sweating, okay? So sweating bullets, right? But yet no work is being done. So how can we understand if this makes any sense? Well, if we take our, entire system, which includes everything, and so we split it into, say, the block, which can store energy in the form of kinetic energy, and we have U. Okay, so this is sort of like everything involved in the situation here. And you can store energy in various different forms. You can store energy in chemical form, you can store energy in thermal form, like that. Okay, so what's happening in this situation is, sure, there's all kinds of interesting stuff happening over here. There's all kinds of transfers of energy happening within your own body. Chemical energy, so we say, chemical energy in your body is going down as thermal energy goes up. Okay, so there's sort of down and up here, so that the total inside your body remains the same, but there's no transfer. So normally we say, yes, work done. There's a transfer of energy to the block, and so the kinetic energy of the block will go up. Well, the kinetic energy of the block didn't go up, and so there's no transfer, and so there's no work done. So all that's happening is, if we think about energy storage mechanisms, we say that in this isolated system, the total energy can't change. So what are the components of that total energy? Well, there could in principle be a change in the chemical energy in your body. There could in principle be a change in the thermal energy of your body. There could be in principle a change in the kinetic energy of the block. But in this case, no work was done. No energy was transferred to that block. The kinetic energy of the block didn't change. So this is just 0. Okay? Whereas your thermal energy went up, you're heated up, you're sweating. So that delta E thermal is a positive number. And in order for these two things to add to 0, then delta E chemical must be negative. Your chemical energy changed, it went down, and your thermal energy changed and it went up, such that the change in the total energy inside you was 0, and there's nothing transferred to the block, no change there. Okay, so that's all that's happening in that situation. Okay, so it does make sense when the displacement, when you push on a wall, you're doing no work. You're not transferring energy to that wall. Okay, so the second example, in the second example, we're going to imagine that the displacement delta R is perpendicular to the applied force. Say force is up, displacement is horizontal. So they're perpendicular. So if that's the case, then our definition says, because the dot product of perpendicular vectors is 0, because cosine of 90 is 0, it tells us that also the work done is equal to 0. And so that means work done is energy transferred. No energy has been transferred. So the energy, remember, work is an energy transfer mechanism. If the work is 0, there's no, same thing as saying there's no energy transfer. Okay, so a nice example of this is we've got this same block and this same little person here. So we've got a block, and there's a person who is who is exerting a force on the block upwards like this, holding the block up. So there's a force. So the person is holding the block up, but not only that, that person is walking with the block. And that person is walking with a constant velocity, just holding up that block. And so, you know, sometime later, the block ends up over here. So there's been a displacement of that point on the block from there to there. And so our displacement vector is delta r, is that guy. And so the important thing here is, because there's a force only in the vertical direction, and what is that force? Well, that's just negative the weight. So the upward force is canceling the weight, so there's no net force in the vertical direction, there's no acceleration in the vertical direction, the block is just moving horizontally. But there's also no force in the horizontal direction, and so there's no acceleration in the horizontal direction, there's no change in the velocity. So whatever initial velocity this block had, it has the same final velocity. So there's been no change in the speed of the block. So there's been no change in the kinetic energy of the block. There's been no energy transfer to the block. And so there's been no work done on the block. Okay? So the energy transfer is 0, the work done on the block is 0. Okay? And so, but nevertheless, it sure feels like you're doing work. You know, you carry this heavy box. You know, you're burning chemical energy, you're sweating, you're heating up. Okay, but it's exactly the same thing as this situation. We've got the block and we've got you. Okay, so no energy has been transferred to that block. The block can only store kinetic energy. Its kinetic energy hasn't changed. No energy has been transferred. No work has been done. All that's happened is chemical energy has been converted into thermal energy. You lost 10 joules of chemical energy and you increased 10 joules in thermal energy. And the total energy remained in that isolated system here remained the same. Energy is a conserved quantity. It can never be lost. Okay? So, yeah. So that's it. I feel like I wanted to say something more here. Oh, yeah. So in order to make this like really clear, in both of these situations, let's say this situation over here, okay, so what's happening, it feels like you're doing work, but that's just because you're inefficient. What we could do is we could replace you with a compressed spring. Okay, and that compressed spring just sits there static and exerts this constant force on this block. Well, nothing is happening. Nothing interesting is happening. There are no energy transfers happening anywhere. No work is being done anywhere. Okay, the only reason why it feels like you're doing work is because human beings are inefficient creatures, inefficient machines. Okay, and similarly here, it sure feels like you're doing work, but remember that we can replace you, this inefficient machine, with a little table, a little cart. A little cart with frictionless wheels, and that block is rolling on this cart with frictionless wheels. It has some initial velocity of 2 meters per second to the right. It will always have that velocity of 2 meters per second to the right because there's no net force. The table pushes up, weight pushes down, no net force, velocity remains constant. There's no change in the kinetic energy of the block. Nothing interesting is happening here. No transfers of energy are happening. Okay. So let's consider the third case. So the third case is exactly the same as this case, except we're going to allow the person to have a component of force that is in the direction of the displacement, in the direction of motion of the block. Okay, so now our situation looks like this. We've got a block, and we got a person, and this person is exerting a force on this block, and that force is in some general direction like this. It has a vertical component. The displacement will be this way. So it has a vertical component that's perpendicular to the displacement, and it has a horizontal component that is F parallel to the displacement. And the block, a little bit later, ends up over here. So the block was displaced from this location to this location. So the displacement vector, delta r, is this guy. And the angle between the applied force and the displacement vector is some angle theta, like that. So now in this situation, if you look at it, you say, ah, yes. So this perpendicular component of force just cancels the weight, and so there's no net force in the vertical direction, and the block only, no acceleration in the vertical direction. Okay, in the horizontal direction, though, there is a component of force in the net force in the horizontal direction, which will be causing the block to accelerate in the horizontal direction, pick up speed, and hence the block will have more kinetic energy here. So it might have started out moving with a small velocity, v initial. It ends up moving with a larger final velocity. So indeed, the kinetic energy final is larger than kinetic energy initial. Delta kinetic energy is positive. There indeed has been kinetic energy transferred to that block. There has really been a transfer of energy. So in this case, we calculate, we say, ah yes, well, the work done is F dot delta R, vector dot product, and the force has two components, perpendicular and horizontal, perpendicular and parallel, so perpendicular plus parallel to the displacement, vector dot product with delta R. And then you look at this, F perpendicular dot delta R, well, that's that vector dot that vector, well, that's just zero. Perpendicular vectors have a zero dot product. And so, and then all we have is this parallel, the force parallel to the displacement. So that vector dot product is just the magnitude of this times the magnitude of this times cosine of the angle between them is just zero. So it's just the magnitude of this F parallel component of the force. That's the only one doing work, the only one transferring kinetic energy to that block, times the magnitude of the displacement. And suppose that this distance here is d. Okay, so that's just F parallel times d. And then what is F parallel? Well, F parallel is this horizontal component of that force. So if this is the hypotenuse of the triangle, this bottom side here is the hypotenuse F times cos theta. Okay, so it's just F times cos theta times d. And so the work done is F d cos theta, which makes sense. Okay, so in this case, what's happening, if we think about, say, from the point of view of energy storage mechanisms, so we'll say, yeah, we can write the idea of conservation of energy as the total energy in an isolated system never changes. And so we say, well, what are the various ways in which nature can store energy in this problem? Well, one of the ways is certainly kinetic energy of this block, energy of motion of that block. So there could be, in principle, a change in the kinetic energy of the block. Okay? And then we think about, well, what else is in this entire system? Well, there's U, and U can store energy in various forms. And so, for example, chemical energy. And so that chemical energy could, in principle, change. And you can also store energy in the form of thermal energy, and in principle, that could be changing. Okay? But the sum of these three changes better add up to zero. So in this case, what we have is there is, in fact, an increase in the kinetic energy of the block. So the change in the kinetic energy is a positive number. There is also an increase in your thermal energy, because you're also going to be sweating when you're doing this, right? So there's going to be an increase in your thermal energy, so the change in the thermal energy will be positive. Well, here we've got two positive numbers, plus this thing has to be zero. This thing better be negative, and that makes sense. There's been a change in your chemical energy. It's gone down, so the change is negative. And so those two positive numbers and that negative number add up to zero. So your chemical energy has gone into two different forms of energy. So some of that chemical energy went into heating you up, and some of that chemical energy went into increasing the kinetic energy of the block. And so now when we go back to this picture over here, then we've got the block and U, and yeah, some of the chemical energy has gone into thermal energy, but some of that chemical energy has also gone into kinetic energy. Now there really is a transfer of energy from U to the block. Okay, and so there really is work done on the block. Okay, great. And so the fourth example that we'll look at is the case where the force and the displacement are at an angle greater than 90 degrees. Okay, so how should we write this? Theta is greater than 90 degrees. And so that's going to tell you, so the picture kind of looks like this. Maybe this is your displacement, delta R, and your force has an angle that's greater than 90 degrees. So in that case, remember that the work, force dot displacement, that when the two are less than 90 degrees apart, the dot product is positive. It's 0 when they're 90, and it's negative when they're greater than 90. So the work done will be less than 0. It will be negative. So if you've got a block and it's got some kinetic energy, it means that the work done by that force on that block is negative. It has transferred negative energy to the block, so the kinetic energy has gone down. Okay, so simple example is something like this, where we've got say a horizontal frictionless surface here, and we've got a block, and that block has some initial velocity, v initial, to the left, and there's a person standing over here. Okay, and so that block is coming at the person. And so what the person does is the person pushes on that block this way and slows the block down and brings it to rest momentarily. Okay, and so we're going to imagine this person has very long arms, okay, and is applying a constant force to the right like that. And so the initial velocity is in that direction, the force is in that direction, the acceleration is in that direction, and so the velocity remains in that direction but gets smaller and smaller and smaller. And then when the block, say, gets over here, the block, say, v final, is equal to 0. The block comes momentarily to rest here. And then, of course, if v continues with that constant force, the block will then speed up to the right like that. Okay, so in this situation, we have, oh yeah, so there's a displacement here. So the displacement of that point in the block went from there to there. The displacement vector is delta r, like this. Okay, so the force is in that direction, and the displacement is in that direction, and so the angle between them is 180 degrees. Remember that cosine of 180 degrees is -1. So in bringing this block to rest, the work that you do, what is that work? Well, that work is equal to force dot delta r, and the force that you apply is, well, this constant force of magnitude F, and the displacement, the magnitude of the displacement, let's call that as usual d, so it's going to be F times d times cosine of the angle between the force and the displacement. Well, that's 180 degrees, and cosine of 180 degrees is -1. And so the work that you do is negative FD. So the point is that that work is negative. Okay, so you have indeed transferred energy to the block, but you've transferred a negative amount of energy to the block in such a way that the kinetic energy was reduced from some value 1/2 mv initial squared down to 0. So, so the change in the kinetic energy of the block is, 1/2 m times v final squared minus v initial squared. V final is 0. You brought the block momentarily to rest, and so this is negative 1/2 mv initial squared. Okay, so the work that you did is negative, and the change in the kinetic energy is negative. In fact, they're equal. Okay, so you have transferred negative energy to that block. So in terms of conservation of total energy, it's a similar kind of situation like this. So well, let's just write it down. So 0 is equal to change in the total energy of everything, of this isolated system. So there are various ways in which energy can be stored in this situation, exactly the same as this. There can be energy can be stored in kinetic energy of the block, and so in principle that could change. Energy can be stored in chemical energy inside your body, and so that in principle can change. And energy can be stored in thermal energy, say, inside your body, and that in principle can change. So in this case over here, what we have is the change in the kinetic energy of the block is negative. It started with kinetic energy, it ended with none. So 0 minus something is a negative number. So the change in the kinetic energy is negative. It got reduced. Thermal energy, again, this is going to involve some sort of internal effort on your part. Okay, so there's going to be an increase in the thermal energy. Okay, and so now there's also going to be a change in your chemical energy. Okay, and that chemical energy is going to also go down. So this last situation is really interesting. You can see that this last situation is identical to this situation, except that in this situation, the change in kinetic energy is positive. Okay, the block picked up speed. There was kinetic energy, positive kinetic energy transferred to the block. In this situation, the change in kinetic energy was negative. So kinetic energy was removed from the block. It was brought to rest. Okay, and so let's look at this term over here. So certainly your chemical energy is going to go down. You're going to use up chemical energy applying that force against that block coming at you to bring it to rest. Okay, so that's sort of the same here and here. However, in this situation, because delta kinetic is now negative instead of positive, for this whole thing to add to 0, it means that this guy, the change in your thermal energy, has to be even bigger than it was here. So this is like a double plus sign over here. Okay? And so why is that? Well, basically, just imagine that you've got instead of a block moving like this, you've got a ball of putty. And instead of a person bringing it to rest, let's just say it's a wall bringing it to rest. I take that block of putty, or that ball of putty, and I throw it at the wall. It sticks to the wall. Okay, and what you notice is that, oh, the temperature of the putty went up and the wall where it was touching. Okay, and so what has happened is nice ordered kinetic energy in that ball of putty like this has been converted into disordered thermal energy associated with the kinetic energy of motion of, increased kinetic energy of motion of all the atoms inside that ball of putty. Okay, and so you can do that experiment. You just throw a ball of putty at the wall and you can see that it heats up. Okay, the same thing is happening over here. Okay, so you take that block and you throw it against a person like that, and that person is inefficient. And what's going to happen is all that nice ordered kinetic energy will just be converted into disordered thermal energy. Okay, so that kinetic energy that decrease in kinetic energy, a lot of that really goes into increasing your thermal energy more than it would increase in that situation. So that's kind of cool. So again, what we should really do is we should replace this super inefficient machine called a human. We should replace that with just a spring, okay, an ideal spring. So this spring is sitting here, it's uncompressed. The block is coming in like this, it hits that spring and it compresses that spring. The spring exerts a force that way, reducing the speed of the block momentarily to 0. At that instant of time, all of that nice ordered kinetic energy has gone into nice ordered field energy inside the spring, which can then be re-released, okay, and converted back into kinetic energy by just letting the block now sitting against a compressed spring allow the spring to uncompress and accelerate that block again up to exactly the same speed it had before it hit the spring. So you just convert kinetic to spring potential back to kinetic, with no energy having gone into thermal energy here. Okay, this is actually, there's a lot of cool physics in this example, actually in all of these examples, but this is kind of the coolest. Anyway, so at the end of the day, what we see is that this generalized definition of work done, effort expended, makes sense. Work, and also in terms of the energy transfer. Remember that work is an energy transfer mechanism. And this definition makes sense, and we're happy with it. And we're going to go forward with that. Okay, so we have now generalized, deepened our understanding of work, transfer of energy by the action of a force acting through a displacement, where the force is a general three-dimensional vector, and the displacement is a general three-dimensional vector displacement. And so it's the vector dot product of the force and the displacement. So that's a very good generalization. However, it still is not completely general, because it still assumes that the force is a constant vector. Okay, so like gravity is a constant vector. So if I throw some trajectory up, or no matter what trajectory an airplane is under or whatever, the force of gravity acting on it is constant. It's always of magnitude mg pointing down. It's a constant vector. Okay, so far this definition works for constant forces. But of course we would like to generalize it to non-constant forces. Okay, and that'll be the final generalization that we're going to do. Okay, but how are we going to do this? So let's just think about this for a minute. Let's imagine, say, an airplane or whatever moving on some three-dimensional trajectory through space like this. And so relative to some origin point here, say this is the initial position, and this here is the final position, or final. Okay, and let's suppose that there's some force acting on the airplane. Okay, maybe it's wind, or maybe it's I don't know, it's not gravity, maybe it's thrust forces or whatever. There's a variable thrust force, say, acting on the airplane. Okay, and so maybe that thrust force initially points, say, in that direction, and then sometime later the thrust force points, say, in a different direction, say with a different magnitude, and then over here, again, it's different direction, different magnitude, and so the force that's acting is different at different points along the trajectory. So now the force is no longer constant. Okay, so the first question we ask is, would this definition, would this formula make sense? Well, let's see. We know what delta r is. That's easy. Delta r is just the vector which points from r initial to r final. So that's that vector. That's delta r. Okay? That's r final minus r initial. But the question is, what force are we going to use? We know delta r, but are we going to use this force? Are we going to use this force? Are we going to use this force? The force is always changing along here. It's not obvious which force to choose. Some kind of an average force? What are we going to do here? Okay, so one clue is we know that this formula works and makes perfect sense, gives us reasonable answers when the force is constant. Okay, well, we can imagine that if this delta r is not a big long delta r like that, but is a very, very small delta r. So let's imagine that the airplane goes from here to here. So initial position is here, final position is here, and so the delta r is now really small, and we'll call it a dr. So delta means a finite change in r, d as in calculus means an infinitesimal change in r. And then the idea is, well, you know what? As that infinitesimal displacement gets smaller and smaller and smaller, that force is going to remain basically constant over that infinitesimal displacement. It changes over finite displacements, you know, maybe quite a lot, but over an infinitesimal displacement, it's going to change negligibly. And in the limit that dr goes to 0, in that calculus limit, the change in f will be 0, and f will really be constant. So this formula will work over these small intervals. And so we can say, yeah, how much work has this force done as the airplane has gone over this whole trajectory? Well, what we would do is, let's start with it having gone over this little part of the trajectory. So it'll be the force at that point on the trajectory, vector dot product with the displacement from there to there. That's true, okay? But now we have to repeat this process everywhere along. Okay, so we have to repeat it. We have to start over here, over this little infinitesimal interval, then this one, and so on. We divide the whole trajectory up into small little drs. So here, for instance, the dr from here to here is that little vector, and the force is that one. Here the dr is that little vector, the force is that one. Okay? And so what we really need to do is calculate f dot dr at every single point along here, and then sum. And remember that in calculus, a sum is written as a curly s here, is an integral symbol. And so we integrate f dot dr. So if you know about integration, that's what it is. And so then the work done is equal to the integral of f dot dr over that whole trajectory from the initial r initial, to the final r final. Okay, so this is a definition for work or energy transferred to that object by that force acting over that whole long path like that. But the problem is it requires calculus, and in general that's difficult. However, there is an important case in which there are two important cases, and one is what we've already seen. If the force is constant, maybe we're just talking about the force of gravity. So that's that force here, that. So at every single point along the trajectory, the force is actually, has the same magnitude and direction. If that's the case, so if we take our most general definition here and apply it to the case of constant forces, it better reduce to that. Well, let's see if it does. So if the force is constant, okay, then this definition for work says, f dot dr, but the force is constant, and we can pull a constant outside of the integral. And so that's just this constant, say gravitational force, vector that we pulled out of the integral, vector dot product with the integral of dr from r initial to r final. Okay, so what does it mean to integrate dr? Well, it means to add up that little dr plus that one, plus that one, plus that one, plus that one. If we add up all these infinitesimal displacements, add those vectors tip to tail, well, obviously we get a vector pointing from here to here. So that is really just delta r. So that's, this integral of dr is just delta r. And so in the case of a constant force, we can pull it outside of the integral, and our most general formula or expression for work reduces to our special case when the force is constant. Okay, so that's very good. Okay, this integral is an expression for the work done, the energy transferred to our airplane by a non-constant force acting over a whole bunch of infinitesimal displacements. Add up the work done over all those infinitesimal displacements to determine the net work, the total energy transferred to the airplane by that non-constant force acting over its entire trajectory. Okay, and that's all very fine and well. The trouble is, until you guys know more calculus, this expression is basically useless to you. However, it turns out that if we shift our focus from an individual force, for example, say the thrust force, and the work that the thrust force does over that trajectory, to all of the forces, the net force, okay, the work done by the thrust force, plus the work done by the gravitational force, plus the work done by wind resistance, plus the work done by lift of the airplane, and so on. If we look at all of the forces acting over that trajectory and figure out the work done by all of those forces and add them all up, then this integral turns out to be very easy to do if you know a little bit of calculus, and you get this exact, very general, very powerful result called the work kinetic energy theorem. Okay, and so this is a powerful and useful result. So let's derive it. Okay, so let's imagine that we have an airplane flying around in three-dimensional space, and you know, relative to some origin point O here. Let's suppose that the initial position of the airplane is this. This is our initial at some time t initial, and then the airplane flies along like this, and then this is its final position. So this is our final at some time t final, like that. Okay. Now, at one particular instant of time, say pick this time over here, let's call that time t, the position of the airplane is this. This is r, the position of the airplane at time t. Now, the velocity of the airplane at that time, velocity is always tangential to the trajectory, so it'll be some vector like this. So let's say that's the velocity of the airplane at that instant of time t. And now the idea is that velocity is changing. Okay, and so there's an acceleration involved, and that acceleration is produced by forces acting on a mass. Okay, so we'll give the airplane some mass m, like this, and we will draw a free body diagram showing all of the forces. Okay, so we have an object, which is our airplane, of some mass m, and we will imagine all of the forces acting. So we think field forces. So there's going to be a weight pulling down. So there's going to be a force of gravity. And that force is in fact going to be constant, so that one's easy to deal with. But then there are non-constant forces. So there's going to be a force of friction, there's going to be wind resistance, and that wind resistance acts backwards. So there's going to be a force of friction, or a drag force, whatever you want to call it, drag force. And in order to overcome that drag force, we certainly need a thrust acting in that direction at least. So in the direction of motion usually is the direction of the thrust force from the engines. And then the wings of the airplane, they also offer some lift. Okay, and suppose it's just sort of in three-dimensional space, it's curving around like this, and so the lift is, say, in this direction. So there's a force of lift from the wings, and so on. That's basically kind of the forces that would act on an airplane. And the idea is all of these forces, the net force, must add up to a force in the direction of the acceleration. So let's suppose that the acceleration is, say, in that direction at this instant of time t, because the velocity is basically curving this way, so there'll be a component of force that direction, and maybe it's also picking up speed, so there's a component of force that way, or acceleration that way. So the net accelerate, or the acceleration might be in that direction. And so that's due to this net force. So the net force should act in the direction of the acceleration at that instant of time. Okay, so we have that. And so that acceleration, we have the sum of the forces, the net force, at any instant of time t is equal to mass times the acceleration of the airplane at that instant of time t. Okay, very good. So that's our general situation. And now what we want to do is we want to figure out not only what is the work done by the force of gravity as the airplane goes over its trajectory, but we want to add that to the work done by the thrust force over its entire trajectory, plus the work done by the drag force over its entire trajectory, and so on. Okay, so we want to add up all of the work dones. We want to add up and determine the net work done, or the total work done. Okay, so the total work done, so the work done by all of the forces, force of gravity, thrust force, and so on and so forth, that total work, the work done by the net force, is going to be this integral over here, but we replace that single force with the sum of all of the forces. So it's all of the forces added up at some instant of time t, and we vector dot product that with an infinitesimal displacement at that instant of time t, dr dt. And then we add this up, we add up all of these works done over all the infinitesimal displacements along the whole trajectory from r initial to r final. Okay, great. And then what we do is we say we use dynamics first. That's the first basic principle that we use here. We know that the net force, the sum of all the forces, is mass times the acceleration of the airplane. Okay, so we have, this is mass times acceleration at that instant of time t, and then we vector dot product that with dr at time t. Now the trouble with this, what makes it difficult, is this is an integration over three-dimensional vectors. You know, the vector r is a function of time. And so that's a complicated kind of integral to do. So what we're going to do is convert the integration over the position vector r to an integration just over time from t initial to t final. And so we do that by recognizing that, well, r depends upon t. So dr is the same as dr dt times dt. Okay? And so we're no longer integrating from the vector r initial to vector r final. Our integration variable is t. We're integrating from t initial to t final. Okay, so that's a huge simplification already. Then what we recognize is two things. We're integrating from t initial to t final. We have the mass m. We have that the acceleration is the time derivative of the velocity. So that's just dv dt. Vector dot product with, well, what's dr dt? Well, that's just the velocity, v, at the instant of time t, and then dt. And then we look at this thing and say, well, this is like the derivative of a function times the function. Okay, so you remember from the product rule of calculus, the derivative of a product of two functions, f and g, is df dt times g plus f times dg dt. If it's not just f times g, if it's just f squared, then we know that that's the same thing as saying that the time derivative of the square of a function is the same thing as twice the time derivative of the function times the function. Okay? And that's exactly what we see here. We have the time derivative of a function times a function. So the time derivative of a function times a function is equal to, bringing the 2 down here, 1/2 the time derivative of the function squared. Okay, so we have the m from before. We get a half from here, pulling the 2 down to there. And we get a time derivative of f squared, or a time derivative of the vector v, vector dot product with the vector v. So this is the time derivative of v vector dot product with v. And that's integrated over time. Okay? And v dot v, well, that's just the magnitude of the vector v squared. That's just the square of the speed. Okay? And so this is the same thing. We're integrating from t initial to t final. So this is the same thing as, we can pull the half m out of the integral. This is 1/2 m times the integral of, so d by dt of v squared dt is the same thing as just the differential, the d of v squared. Okay, and so now our integration variable has changed from time to just velocity. Okay, and so what this is saying is the total work done is just 1/2 the mass times the sum of all the little changes in v squared. Okay, so how much did v squared change in going from here to here? Add that to how much v squared changed in going from here to here, and so on. And so at the end of the day, all you get is this integral is just v squared at the final point, vf squared, minus v squared at the initial point, v initial squared. Okay, so this just becomes 1/2 m times v final squared minus v initial squared. Oh, wait a minute. That's just kinetic energy final minus kinetic energy initial. That's just change in the kinetic energy. Okay, so this is a very powerful general result. Okay, so individually, these integrals are hard to do for the individual forces, but if you add up all the forces and do the integral, you find that the work done by all of the forces together, the total work done, is simply the change in the kinetic energy. So this is the work kinetic energy theorem. So the total work done, or the net work done, is equal to the change in the kinetic energy. This is a very powerful, very, very powerful result. So what makes this result so powerful is that it is valid for arbitrary forces. Okay? So those forces in particular need not be constant. So they can be very, very complicated. They can depend upon time in a very, very complicated way. They're valid for arbitrary forces. Okay? However, you must include all forces. This is total, the work done by all of the forces. You have to sum up all of the forces. So you must include all forces. Okay, so like this. So you have to draw a free body diagram showing all of the forces that are acting and make sure you know what they all are. Okay, and then you can work out the work done by those individual forces, and that should be the change in the kinetic energy of the object. So as powerful as this result is, it's also obvious, because when we say that some of the forces is mass times acceleration, and so that acceleration is changes in velocity and so on, we're really just talking, in terms of energy, we're just talking about kinetic energy. So it's basically a point particle, and the only way that a point particle can store energy is in its kinetic energy. And so if we are applying forces through displacements, if we are transferring energy to that airplane, well, then the only place it can go is into the kinetic energy of the airplane. And so sure, all of the energy transferred to that airplane, so the work done by gravity, the work done by lift, the work done by drag, and so on, all that energy, positive and negative, transferred to that airplane over its whole trajectory is just going to go into the kinetic energy, decreasing and increasing, decreasing the kinetic energy. So this result is obvious. Okay? It's just sort of a special case of conservation of energy. You put energy into something that can hold only kinetic energy, well, obviously the kinetic energy is going to go up by that amount that you put in. Okay? Nevertheless, it is very powerful, and we'll see how to actually use it to solve some interesting problems. Okay?